Okay, so this will be a continuation of our understanding of what torque is and how exactly can we calculate what is the torque on any kind of a system that is created by a force. So um, the example that I'd like to take is that of a door fixed to a hinge. Okay, so I had used this example earlier also to discuss the idea of a torque. Let's just develop that same idea further. So this is your kind of looking at the cross section of a door. This is the wall or some rigid object. This is the hinge through which the door will rotate. This is the wooden door, and these are the handles to the wooden door. All right. So now, typically, you would like to ask the question um, where we would apply the force. So let's say that you are applying a force F to the door handle, and obviously you are attempting to make the door swivel in this direction. You are trying to get it to go anti-clockwise. Now, the question that I would like to develop is that um, the force when it is applied at the handle, uh, is it the same? Does it cause the same amount of torque as the same force? I'm trying to use the same kind of distance. It's a vector, so I'd like to keep the same length. The force when it is applied over there. So in case some of you can see it, of course you can see that there is a variation in the distance between these two things, and so therefore you will say that yeah, of course there is a difference because the distance from the axis of rotation has reduced, so therefore the torque should also have reduced. One way to answer these kinds of questions is, of course, to go to the absolute absurd, which is that what will happen if you apply the same force at the shortest distance possible to the axis of rotation. Okay, um, so let me just put this axis of rotation, right? So then you can see that that's a completely absurd situation, because if you apply a force on the hinge, exactly on the hinge, then it should be impossible to open the door. I mean, you won't be able to move the door, rotate the door in an anti-clockwise direction. You may succeed if you apply a large enough force. You may succeed in breaking the hinge or bending the hinge or damaging the structure in some way. But assuming that that kind of thing won't happen, because if you just apply a force on the hinge, and I suggest you try this actually on the door without hurting yourself if possible, you will see that there is very little torque that is created as a result of that. Now, obviously, we can then say that the torque produced on the system, symbolized by tau, uh, is then the force times some kind of a distance. Okay, and the distance we've kind of said is the distance that is there between the hinge and the place where we are applying the force. So this distance. Okay, and that's your d over here. All right. So now we can ask, um, why is it? Why is this the distance? Right? Why can't, say for example, this be the distance? The distance from the point of application of the force to the hinge. Why not this? All right. for after all, there is going to be a difference, geometrically speaking, between this distance and this distance. Right? This is going to be slightly more than this. So you're going to get slightly a little bit more torque if this is the actual distance rather than this. So what is the actual distance? Well, again, we can go to the same thing that we did before, that is shift the forces, go to the extremes. Okay, what happens when you apply the force at an extreme angle? All right. So there is a suggestion from somebody that the torque will actually be the force times the shortest distance from point of application of force to axis of rotation. Okay, so that's what is being suggested. Now let's see if that works. All right. Okay. So in terms of defining what this distance actually is, let us see what happens when we change the direction of application of the force. Is it going to be the same if I apply the force, the same force, at this angle? Or at any angle along that line, including the most absurd option that is possible, which is to apply it tangentially. Let's say like that. Okay, so I apply the force like that. Now you'll say that, well, that's silly, because if you push the door in that way, you're not going to achieve any anti-clockwise movement, right? And now it bears the question, why doesn't it achieve any anti-clockwise movement? Because torque, for it to be available, has to be F times the distance. The force is there because you're applying the force on the door handle. You feel it in your hand. You're applying the force, you're pushing, right? But there is no torque being created, probably because the distance is not there. But then you're still applying it on the handle. So what distance is not there now over here, right? So the distance that is not available over there, I suggest to you, can be looked at like this. So what you can do is you can look at the line of application of the force, which is, to go back to this proposition, right? The shortest distance from the point of application of force, you're tweaking that a little bit, because if you say point of application of force, that's there. So there is a distance from there to the hinge. So that's not quite right. But if you take this as the line of application of force, I'll use a different color to show the line of application of the force. So the purple line indicates the line of application of the force. Okay. Then you can see that the distance between the hinge and that the shortest distance, I'll just get rid of this part of it now. So the shortest distance between this has now reduced considerably. And you can imagine that if the force were being applied in such a way that the line of application of force passes through the hinge, right? Like if you applied the force in this manner, and I have to construct this, because what we are discussing is a situation where there is going to be no torque, right? So the no torque situation would of course be this. Not this one, but this one. So then what happens is that since the line of application of the force is such that it passes right through the hinge, right? So what will happen is you will start pulling it. What will happen is it will turn a little bit, and then it will come into such a position that the line of application of force, when it passes through the hinge, it will not turn anymore. Okay. Why does it not turn anymore? Is that the line of application of force now has zero distance with the axis of rotation. The d has reduced to zero. And when the d reduces to zero, the torque disappears. So when the torque disappears, there is no rotational motion possible, because right now it is in equilibrium. It's in static equilibrium. Sigma f is equal to zero, so therefore it will not rotate. And of course, that is also what happens in the previous situation with the scale that we had discussed. What about the situation when the scale, which has some rotational inertia, which means that you have hung an object, right, in such a way that there is a lot of, in this case, torque in this direction, right, which is anti-clockwise torque. Then the object comes to hang in this kind of a manner. This is the scale, this is the stone, and that is the string. So now what happens is that the line of action of the force, so it's the gravitational force, right? The gravitational force is pulling it in this direction, mg. The line of action of the force will pass through the axis of rotation, right? So when that happens, again your torque reduces to zero, because mg is there, there is a force, but the distance has reduced to zero. So therefore it comes to dynamic equilibrium. Okay. So therefore we can now modify our statement, the above statement over there, that torque on a system will be equal to the forces acting on that system multiplied by the shortest distance from, not the point of application, we'll have to change that. We'll change that to line of action of the force, and then you don't need to specify to the axis of rotation. So that's how you define torque, and of course the units for this will be Newton multiplied by meter, which you of course realize is work done. So how does that add up, and what implications are that, we will see in the next video.